everyone. I hope you're having a good day. And today I would like to derive Gauss's law for the electrostatic field from Coulomb's law. So consider we have the origin of our coordinate system right here. We have the x-axis, y-axis, z-axis. We have some point charge, say, right here, and it has a charge q and a position vector r prime. Now consider we want to know the electric field at some point in space, some point out here. Let's call it P. And then this point is going to have its own position vector r. And we know from Coulomb's law that the electric field due to a point charge is equal to 1 over 4 pi epsilon naught times the charge q divided by the distance between the place where the charge is and the point P squared. So I'm just going to draw a new vector, one that points from the point itself to, or from the charge itself to the point where we're trying to calculate the field. And this I'm going to denote with a little squiggly r, where this is equal to the r vector, which is the vector out to the point of interest, minus r prime, where r prime is the vector out to the point where the charge is located. So this is the magnitude of this r vector is the distance between those 2 points. So the electric field depends on the charge divided by the square of that distance, and it points in the direction of r hat. So if we have, this is kind of our r hat, and this is the electric field of a point charge. But there are a lot of things in nature that aren't point charges. You know, we have a lot of actual 3D objects where we can't just treat them, especially at close distances, as a point charge. So we really want to be able to figure out a formula for the electric field of some three-dimensional object. So consider now the same kind of coordinate system set up, x, y, z, but instead of having just a single point charge, we have some object in space, and we want to calculate the electric field at some point P, distance r from the origin of our coordinate system. So how we can approach this is by taking this object, say it's a charged object, and consider just a little tiny cube within the object. And say it's a cube that's small enough that we can treat it as if it were a point charge. This cube here is going to have an amount of charge dq, and it's going to take up volume d tau prime, and it's going to be located at the vector r prime, and where the prime notation is just a way of saying that this is associated with this point in the space, as opposed to just the point where we're trying to figure out the field. So points within our three-dimensional object are going to be denoted like an r prime or a tau prime, whereas here we're going to have just our regular r. So then, from this cube to this point, we're going to have our vector r as usual, and we know that from this one little cube of charge, that our little infinitesimal electric field coming from that is going to be 1 over 4 pi epsilon naught times the amount of charge, which is dq, r squared times r hat. And another thing we know is that the electric field is a vector, almost like the force or something like that. So it follows the superposition principle, meaning, say we have two point charges, Q1 and Q2, and we have a point P. If we want to find the net electric field at point P, let's call it EP, it's going to be equal to the vector sum of the field from charge Q1 plus the field from charge Q2. So if we want to find the total net electric field caused by this object, or being created by the charges in this object, what we want to do is take every single piece of the object, every little cube within the object, find the electric field from that, and then add them all together. So how we're going to do that is by integrating over the total volume of the cube, of the object, which is going to take all of the cubes, add them up, or the electric fields from the cubes of charge, add them up, and give us the net electric field at our point. So what we're going to want to do is we're going to want to integrate over all of the charge elements in our object. The one before perhaps on is constant. So we can pull this out to the front of our integral. We have dq over r squared, r hat, behind the integral. And another thing that we want to do is generally we don't want to integrate over a charge. We want to integrate over positional variables. So say that we know that our object has some charge density, rho, of r prime, is the charge density. So if we know that this is the charge density, then we know that the infinitesimal charge at our given point is going to be the charge density at that point multiplied by the little volume element. So we have that dq is equal to our rho, which is the volume charge density multiplied by our volume element. So now we can rewrite our electric field in terms of a volume integral over the entire surface, as opposed to just an integral over the charge. So let's do that. We end up with E is equal to 1 over 4 pi epsilon naught. Now we're going to have the volume integral of rho of r prime over r squared r hat d tau prime. And this is the integral that we can use to calculate the electric field over some charge distribution, or some volume charge distribution. And note here that the r squared and then the r hat, the way it was defined, we have it equal to vector r, which for this given point is going to be constant, minus r prime, which is changing over the integral. So these vectors, or well, in this case, it's the magnitude of the vector, and in this case, it's a unit vector, can't be pulled out of the integral. So what we end up doing is integrating over the prime variables of just the charge density divided by the square of the distance between that little cube and the point P. Okay, so now, what do we want to do next? Well, I said my goal today was I want to derive Gauss's law. Gauss's law says something about the divergence of the electric field. So I want to calculate the divergence of this. So we know that the electric field is a function of r. We have our vector r to our point, and we want to take the divergence of this. So we're going to take the divergence of the electric field E is equal to, and now we want to take the divergence of this function. It's going to be the divergence of 1 over 4 pi epsilon naught times the volume integral of rho of r prime over r squared r hat d tau prime. And then something to note is that since this is a function of r, this divergence is with respect to r rather than squiggly r or r prime. And then the same thing with this divergence. So now this is a constant. We can pull this out to the front. So we have this 1 over 4 pi epsilon naught. And now, since this volume integral is over the prime coordinates, and this is a derivative over the r coordinates, we can pull this derivative inside of the volume integral. So doing that, we end up with the volume integral of the divergence of rho of r prime, r hat, over r squared, d tau prime. And then one more little thing we can do is noting this is divergence with respect to r, and this is a function of r prime. This is also going to be constant with respect to this divergence. So we can pull this function, the charge density, outside. So we have that the divergence of E is equal to 1 over 4 pi epsilon naught times the volume integral of rho of r prime times the divergence of r hat over r squared d tau prime. So the next step is we want to take this divergence, but note that this divergence is with respect to r, whereas the function is a function of squiggly line. So now, if we take the del operator with respect to r, it's going to be in Cartesian coordinates x hat times the partial with respect to x plus y hat is the partial with respect to y plus z hat is the partial with respect to z. Now consider the coordinates in the r squiggly direction, right? So we have r squiggly is x hat times x prime plus y hat times y minus y prime plus z hat times z minus z prime. And what we have here is a function, the divergence of a function that is a function of squiggly. So really what we want to do is we want to find a way to relate this divergence to this function. So consider just the first component, which is the partial derivative with respect to x of some function. What I can do is I can use the chain rule to rewrite this with the partial with respect to xr, and this here is x sub r, and then use the chain rule to multiply that by the partial derivative of xr with respect to x. And this, the partial x, is going to be equal to partial derivative with respect to x. We see here x sub r is x minus x prime times the partial just with respect to xr squared. So now here, what we have is the partial of x with respect to x, which is going to be 1 minus x prime. X prime in this differentiation is a constant. So this term actually just goes to 1. And we see that partial derivative with respect to x is equal to partial derivative with respect to x1. And then the same kind of analysis is going to hold for y and z. And then the same unit vectors are going to hold. So what we have here is that we can replace these with x hat times partial x r plus y hat partial y r plus z hat partial z r. And this is equal to what we have up here. So these are the same. But note that this, we have the partial derivatives with respect to the r squiggly. It's just the del operator with respect to r squiggly. So we have that this is equal to the del operator with respect to r. So what we can do is we can plug this in here, and we see the divergence of E now is equal to 1 over 4 pi epsilon naught times the volume integral of rho of r prime times the divergence with respect to r squiggly, where we're using this to replace this one, the one in r squiggly, of r squiggly hat over r squiggly squared, and we're integrating again over the tau prime coordinates. So the next thing we need to figure out is, now that we have the right variables, we're taking the divergence of function of r squiggly with respect to r squiggly, we need to figure out what this divergence is. So, in order to do that, and note that this is only a function of the r squiggly. It's not a function of theta or phi, which are the other two directions that we have in spherical coordinates. So what we want to do is we want to take the divergence of this in spherical coordinates. So what I'm going to do is write out the divergence of some vector function, actually let me call it vector function A of r in, yes, r squiggly r would probably do better notation, but in this case, I'm just using this to represent the radial distance in spherical coordinates. So the divergence of A of r is equal to 1 over r squared times the partial derivative with respect to r of r squared times AR of r. Note that this was assuming that this only has a component in the r direction that's only dependent on r. So this could be, say this was A of r theta phi, but only had a radial component, then here you have a function of r theta phi. And now say you had components in either the polar or azimuthal directions, then you would have more terms on this divergence. However, since our function is only pointing in the r hat direction, this is the only term. So now, I want to plug in our original function here. It's r hat over r squared is equal to 1 over r squiggly squared times the partial derivative with respect to r of r squared times, now the r hat component of our vector function is just going to be 1 over r squared. have this r squared and this r squared cancel. We have the divergence. R hat over r squared is equal to 1 over r squared times the partial derivative with respect to r of 1. 1 is constant, derivative of the constant is 0, so this term is 0, and here we have 0. 1 over r squared times 0, 0. So we get the divergence of r hat over r squared is equal to 0, which is a nice result. However, note that this cancellation, where I cancel r squared and then the over r squared, is valid everywhere except at the origin of our coordinate system, where r is 0. Because here we would have a division by 0, and we can't divide by 0. So we want to have another way of being able to check, just make sure that this is the right divergence. And one way we can do that, we can use the divergence theorem. What the divergence theorem essentially says is that if you have the volume integral of the divergence of some vector function, it's equal to the surface integral over the boundary of the volume of just that vector function dotted with n hat dA. So essentially what this is saying is that we have the volume integral of some derivative. The divergence of A is a first order derivative of the vector function, and we're relating it to its behavior on the surface. This is how it is, acting on the boundary. So here we found that the divergence of our function is 0. So the volume integral of the divergence of our function is going to be volume integral of 0 d tau. And now, assuming we have some finite volume, this is just going to give us 0. So what we should end up with is that this surface integral is going to give us 0. So now, this should work for any surface we choose, right? Doesn't matter what volume we have, if the integrand is 0, it's going to be 0. So we might as well choose something that's somewhat simple for us to work with. So what I'm going to do is I'm going to choose a sphere centered at the origin of radius r. So over this volume, we still have the same volume integral. However, the surface integral, we're now going to have the closed surface integral of A, our vector function, is r hat over r squared, dotted with n hat. N hat is the normal vector that points out from our surface. Though since our surface is a sphere, the normal vector is going to be the vector that points radially away. So say this here is our r squiggly vector, the normal vector is going to be that r hat vector. So this dot product, here the n hat is really just r squiggly hat dA. So this is r squiggly hat dotted with r squiggly hat. Dot product of a unit vector with itself is just 1. And now for the bounds of the integral, we're integrating over this spherical surface. So we're going to take the angle theta, which is the angle from the z-axis from 0 to pi. And what that's going to do is that's going to basically cover all the way from up here all the way down here. So what we're essentially doing here is over theta, we're taking and sweeping out a semicircular arc from up here to down here. And then for phi, we're taking that semicircular arc and sweeping it all the way around until we have a spherical shape. So that's why those bounds are the way they are. Also, since it's just a spherical shell as opposed to a full volume sphere, we know that this r squared here is just our known capital R, which is the radius of our spherical shell. So we've got 1 over r squared. And now we want to figure out what this dA element is. And in spherical coordinates, say we have, we draw this r up here instead. Say we have some other r here, or some other point that's such that the angle between them is d theta. So this length here, ds, is going to be r times d theta. So it's this little arc length is related to the radius here and d theta here. And if something similar happens for the phi component, so say this is d phi, but note that this radius here isn't the radius out to the sphere, it's just on the distance out along on the xy plane. So this is going to actually be r times the sine of this angle theta. So here we have r sine theta d phi. So this is r sine theta d phi, and essentially what we have is, we draw it on its own coordinate system, that way it hopefully will look a little bit cleaner. So, got kind of, I apologize, I'm not drawing this well. But, oh gosh, this is terrible. I am a terrible artist. Okay, that's a little better. So this side length here is r d theta, and then this one here is r sine theta d phi. So our dA is going to be just the product of these. It's going to be r squared sine theta d theta d phi. So here we're going to have r squared sine theta d theta d phi. Here the r squareds cancel. We get this surface integral. Is the integral from 0 to pi theta, and then phi equals 0 to 2 pi of sine of theta d phi d theta. Looks like here I have the phi as the inner integral, so this really should be in the order of d phi d theta. But what we have here is, note this integral, the theta integral. We have a function of theta, sine theta. I thought that highlighted this. Okay, we have sine of theta, d theta, is an integral exclusively over theta, and then here the phi integral is exclusively over phi. So we can take these two integrals and separate them out. So this is equal to the integral from 0 to 2 pi to phi times the integral from 0 to pi of sine theta d theta. So this integral here, integral from 0 to 2 pi to phi, is just 2 pi. And then the integral from 0 to pi of sine theta, which is negative cos theta, valued between 0 and pi, is going to equal 2 pi times negative cosine of pi is going to be 1 minus, and then negative cosine of 0 is going to be negative 1. And this is equal to 2 pi times, this is going to be 1, this is going to be 1, this is 1 plus 1 is 2, which is equal to 4 pi. So what we find is that this surface integral gives us 4 pi. And this volume integral we found here gives us 0 for any surface. So we end up in a weird spot where we know that these two things have to be equal, but one of them is giving us 4 pi, one of them is giving us 0. So that's telling us that there's probably something missing, and it's more than likely in this guy. Because remember, when we took the divergence, here we canceled out a couple of r squareds, and we noted that at the origin this might get a little wonky because we're dividing by 0. So we end up with 0 here, but we really should have 4 pi. This is where I'd like to introduce the Dirac delta function. And that's, you have some delta x minus a. What that's going to do is, say we have here the x-axis, right? And here's x equals a. This function is going to be 0 everywhere except for x equals a. And x equals a is going to just spike up to infinity. And it's defined such that the integral from negative infinity to infinity of delta x minus a dx is equal to 1. Or really any integral that includes x equals a. This integral is going to evaluate to 1. So we have like the integral from a minus epsilon to a plus epsilon, where epsilon is some small value of delta of x minus a dx. That's also going to be 1. But say we took the integral from a minus 3 to a minus 2, the delta of x minus a dx, that's going to give us a 0. Because, from a minus 3 to a minus 2, the function is just 0. You have to actually cross x equals a to get that nice peak. Now, another nice thing about the delta is if we integrate from negative infinity to infinity again, the delta function of x minus a multiplied by some function, say f of x dx. If we think about this product everywhere on the x-axis, anywhere that's not x equals a, this delta function is evaluating to 0. We have, at a minus 3 it's 0, a minus 2 it's 0, at a minus epsilon it's 0. So this product is always going to be 0, except for at x equals a. So really, this is equivalent to taking the integral from negative infinity to infinity of delta of x minus a times f of a. Because for every other value where this wouldn't be true, for any f where x isn't equal to a, this is evaluating to 0, this is also evaluating to 0. So the delta function serves to pick out this function at x equals a. But now since this f of a is just a constant, we move it outside of the integral, and then we get just the integral from negative infinity to infinity of our delta function, which is just going to be 1. So this integral here just picks out the value of the function f at x equals a. And this idea can kind of be expanded out to 3 dimensions, where we can have, instead of just delta of x minus a, we can have delta cubed of some r minus r prime. And what this is going to do is it's going to evaluate to 0 everywhere, except where r is equal to r prime. And at that exact position, it's going to spike to infinity. And any integral that includes this range it's just going to pick out the function at that value. So, what if the divergence, instead of just being 0, consider divergence of our function r hat over r squared. If it's equal to 4 pi times delta cubed at r, where this is essentially just saying at r equals 0 is where this fight is going to happen, which if we have our spherical surface, if this is the origin where r equals 0 in the context of the divergence that we're taking. I'll note that in the context of this divergence, this r squiggly is just denoting the distance to a point, as opposed to over here it actually is r minus r prime. But in this case, what we're essentially saying is that the divergence is going to be 0 except at the origin, which if you think about it in the context of like a point charge at the origin, it kind of makes sense because all of the electric field is coming from that one point charge, but not from anywhere around it. So it makes conceptual sense that we would have this delta function at the origin. So now that we know that this is this divergence here, let's plug this back into the electric field, or the divergence of the electric field. Let's plug it back in the equation we have with that. We have that the divergence of E is equal to 1 over 4 pi epsilon naught times the volume integral of rho of r prime. Now this divergence we said is 4 pi. Delta cubed of, and now since we're taking the divergence with respect to squiggly r, this is going to be squiggly r d tau prime. Now here we see there's 4 pi, that cancels that. And what we are left with is that the divergence of E is equal to 1 over epsilon naught times the volume integral of rho of r prime delta cubed of, now squiggly r, remember, for the electric field, we have squiggly r is defined as r minus r prime, was the distance from the charge to the origin. So we have r minus r prime d tau prime. And this, since we're integrating a delta function, is going to pick out the charge density at when this argument to the delta function is equal to 0, and that's going to happen when r equals r prime. So this is rho of r, since we're integrating over the prime variables. So we see that the divergence of the electric field is equal to the charge density divided by epsilon. This is Gauss's law of divergence. In this is actually a really, really cool and really, really handy equation. Because what it tells us is if we know what the electric field is, say we can measure the electric field and we know what that is, all we have to do is take the divergence of that electric field and we know what charge density created it, which is really, really handy and also really cool. There's one more thing we can do with this. And that's, we can apply the divergence there. Remember that the volume integral, the divergence of some vector function A, surrounding that volume of that vector function A dotted with n hat dA. So essentially it relates the volume area of a derivative, or volume integral derivative, to its behavior at the boundary, which is represented by that surface integral. Let's take the divergence of E and just integrate it. So we have the volume integral of the divergence of E, d tau, equal to, and now if we integrate the other side, we end up with the volume integral of rho of r over epsilon naught d tau. Now applying the divergence theorem to this, you see that the volume integral of the divergence of the electric field is going to be equal to the surface integral of just the electric field dotted with n hat dA, which is equal to 1 over epsilon naught, times the volume integral of rho of r d tau. And then what this term here is it's just inside of our surface, or throughout that volume, bounded by the surface, we're taking our charge density, multiplying it by the infinitesimal volume, which gives us an infinitesimal charge dq, and then integrating over that. So essentially what we're doing is just taking and summing up all of the infinitesimal charge elements that are inside of our surface. So what we end up with is that the surface integral of E n hat dA over a closed surface is equal to the charge that is enclosed within that surface divided by epsilon naught. And this is Gauss's law in integral. And this version of Gauss's law can be really helpful for, say, you want to calculate the electric field of a system where you have nice symmetry. For example, like a sphere of charge or a charged cylinder. If you can find some surface across which you know that the electric field is going to be constant, then you can find a way to pull it out of the integral, and it makes it really easy to calculate the electric field. Those cases aren't, there aren't a lot of them, but when Gauss's law in integral form can be used, it is a really, really powerful tool, and same with Gauss's law in differential form. So yeah, that is the derivation of Gauss's law from Coulomb's law for the electric field. Thank you for watching, and I hope you have a great rest of your day.